Okay, thank you. And well, thanks Marius and Julio and all others that were involved in the organization of this event. It's quite intense and I really enjoy it. I'm going to talk about timeless formulation of Wigner's scenario, which I think give us maybe a new insight into the, well, this paradoxical situation that Wigner put forward. This work has been done with Veronica and Flavia, who are PhD students in Vienna. Alexander Smith, kind of external collaborator from Dartmouth College, and Flaminia and Esteban, who were PhD students in Vienna, and now Flaminia is at PI and Esteban at University of Brussels with Ognjen Oreshkov. So let me start with the overlook. I will give kind of a definition of what the quantum measurement problem is, at least for me. The people are not really have the same opinion about that. And then I will just remind you of what is the Wigner-Franz gedankenexperiment, go through very fastly through the Page-Wootters timeless formalism of quantum mechanics, and I'm happy that Philip also introduced this before. And then I will propose different conditional probabilities, definitions for conditional probabilities in Wigner's Franz scenario. And I will say that we don't have any evidences of which of those are true ones. They all agree in the situations which are not Wigner's Franz scenario. We do usually measure in lab, so there is some ambiguity there, which is very interesting. And finally, I will, through the talk, always go back to the question, well, what is the true quantum state? Is there any meaning in that question? Is there any collapse of the wave function? Is this collapse relative to observer, or it's absolute objective? So let me just start with things that we all know whenever, chapter 1, though. It's about the postulates of quantum mechanics. In every textbook that starts with axiomatization of quantum mechanics, we know that there are two postulates that describe the evolution of a quantum system. And in the Cohen-Tanucci and Coulter's book, it's a postulate 5th and 6th. The 5th postulate describes how the state changes in the measurement, and it's related to what we call collapse of the wave function or reduction postulate, the state up the rule. And the 6th postulate is concerns with the evolution of the system or the states in between measurements. And it's governed by the Schrödinger equation. Now, the dichotomy of these two evolutions of quantum states is at the heart of the quantum measurement problem. And that the way how I like to put the quantum measurement problem is that once you have learned about these two postulates, there's nothing wrong in that. Like, you apply one or the other postulate, the problem arises because you don't know when to apply which of them. And this appears first time when you enter a quantum lab. It's a typical quantum optical lab. And you learn about this theory, and you enter there, and you want to predict what the experiment will show. But unfortunately, you don't know where to apply which rule. Like, there are different elements. There are some crystals, the wave plates, photodetectors, beam splitters, fibers. And you would like to know where to apply quantum theory, but you don't know. There is nothing in quantum theory a priori which will tell you where to apply what operation. And then it's through the experience and comparison with your theory that you realize, well, whenever a photon is detected in a photodetector, you rather apply the projection rule as compared with a fiber where you apply the unitary evolution. And this is, of course, related to the question of what makes a measurement. And I didn't want to reveal all these things, but since we had to make it a PDF, I turned all my animations in an immediate picture of everything, so I cannot hide you. But it's really remarkable for me that manufacturers photodiodes know the answer, because otherwise they would not be able to create photodiodes. But we still didn't understand what they do. Okay, so there is this dichotomy, and it's also related to the putting the cat, where you apply the Schrödinger evolution up to the measurement. And in the measurement, there is so-called Heisenberg cut. And it's a cut between the system and the measurement apparatus and observer, and something which we like to call a classical world. And this cut, in my view, should be understood as a functional distinction between object and subject. So it's a somehow a precondition even to make sense out of your experiment, to be able, how Bohr says, to communicate with others. You have to have this cut. And you basically talk about measurement apparatus and everything what is on this side of the cut. This is not a physical cut. This is not, and it's very crude simplification or even a wrong, to my opinion, assumption. It's a physical one between the micro world and the macro world. This is something to be decided in an experiment at the end. But it's a functional one. And since it's a functional one and not a physical one, you can move this cut. And this is the basic of the Wigner's friend experiment. You have two observers. There is a friend. And the friend has a system and a cut between the system and the friend. But from the point of view of a Wigner, the whole system, friend, the measurement apparatus is closed in some sealed laboratory. And what used to be a measurement apparatus for a friend becomes, in this, for external observer Wigner, a quantum system. And I wrote here, in moving the cut, the friend's measurement instrument loses its function and becomes itself a quantum system, an object that can be observed by a further set of Wigner measurement instruments. So there is a Wigner with his cut, which is just shifted from the friend's cut. This picture in Wigner's friend experiment does not deny the necessity of having cut. It's very important. It's not that it's just a unitary picture in which we never ever observe anything. I think it's a wrong view of saying that. And it's quite in agreement with the operational way of thinking. It's just that the Wigner cuts, that what he calls measurement object and what he calls a measurement apparatus is different than what Friends does. And therefore, Wigner can also conclude on the basis of his measurement data. Both of them have measurement data.
Sorry.
Yes?
If I may just ask a question. One of the crucial questions in these kind of discussions is, do you assume, from the Wigner's point of view, that the dynamics inside the box, which includes the friend and all that, is unitary or not?
I will come to this, and I do assume.
Okay.
But this is an empty statement unless this can be confirmed in experiment. That's why I attached here a measurement apparatus for Wigner to even make a tomography and conclude that this was a unitary.
So you're assuming that interference between the friend having measured one thing
and I will heavily use this measurement.
Are observable by Wigner.
Yes,
That's
true.
Precise.
Okay, so here is what is the original Wigner's friend thought experiment. We have a friend who performs a measurement, and I will usually think about the measurement of the spin on a system, and the system is here described by S. So we can think about the system being performed in an X plus spin, which can be written in the Z basis, and spin up and spin down. There is a state of a friend, R, which is nothing else than waiting for the experiment to be done, to learn something. I don't need to specify more these degrees of freedom. But it's, of course, all possible degrees of freedom that could be coupled with a measurement result, like an apparatus, friend's memory, a piece of paper, maybe a PRL that published the result, and everything else. And if I start with this uncorrelated state between the system and the friend, after a while, if I know the Hamiltonian that describes the interaction between the system and friend, I will end up with an entangled state. And I pick up here entangled state with the phase 1. But it's very important. It's not arbitrary phase. It's exactly what Wigner can either learn or know from the conditions of the experiment, or even maybe control. If it will not be the case, it will be a randomized phase, and we will not see coherences. So that's the Wigner's description. It's a unitary evolution from here to here of the system. And as I said, I assume that this can even be confirmed in the subsequent measurement of Wigner. whereas friend observes one or the other outcome, ends up with either spin up or spin down. Now, why it is an interesting situation? Because it appears at first sight, and it's an uncomfortable situation because we have a single physical situation, apparently, and end up with two different descriptions. On one hand, we have an entangled state as described with the Wigner, or something which is one or the other definite state of the spin. Now, one should be a little bit careful here with conclusions. It is a single physical situation, but however, even the system that they refer to is different, because Wigner refers to both system and a friend, and friend refers only to the system. But nevertheless, it's kind of uncomfortable situation. I want now to put this uncomfortability to the extreme in a couple of slides. Now, because you have these two different descriptions, you might ask, well, what is then the true quantum state? And in the papers from a couple of years ago, I was trying to argue that there is actually nothing wrong in having different descriptions by Wigner and friend, and this is very much in line of also what Carlo was proposing in his relational interpretation. And because they respect different experimental situations, they even assign different systems, and that the consequences of that probabilities, even the probabilities, have to be understood as relational, in the sense that their determinacy is relative to an observer. There is no, a mathematical formulation of that is so-called no-go theorem for observation in PAM facts that have been derived in these papers, where you cannot, in the mathematical statement, you cannot assign a joint probability both for Wigner and friend's outcomes, such that the probabilities that friend sees on one hand and probabilities that Wigner sees on the other hand are marginals of this joint probability. There is no such thing. You can disprove in a Bell-type argument. And this is very much in line of the several interpretations, Carlo's relational interpretation, cubism, something which I like to call neo-Copenhagen interpretation. But also, although this is, I'm less sure about that, and I always ask the people who are supporters of the interpretation, but I would say also the many worlds maybe is something in line with this. Now, although I prescribe to this kind of view on the quantum state, I want to challenge this today. And I want to think of an experimental situation in which one or the other observer can convince herself or himself that the state assignment they have chosen is, in a certain sense, incomplete. And I will now go to the concrete experimental situation to explain you what I mean with this, and I will try then to generalize. Okay. There is no doubt that that friend has good state assignment for all the experiments that she wants to perform in the lab. This state is the state that is reduced after seeing the spin up. This is the state she has to use for all other experiments within the lab. And now I ask a little bit different question. What about if I want to make a measurement outside of the lab? Something that Wigner can perform, or some artificial intelligent machine can perform, or something that friend has programmed beforehand and put outside to perform a measurement on a system and the friend. It's a very tricky business and slippery now that we ask both observers to predict this. Why? Because this is a measurement that will be performed on the friend herself. And the kind of measurement that I want to ask is exactly what Carlo mentioned. This was the state at the end after friend performs this measurement on the system, this entangled state. And what I will ask both observers to make a prediction is about the measurement whether the system and friend are in this state or not. So this is a yes outcome. They are in this state. No outcome. They are not in this state. Now, it seems very easy for Wigner to answer this question because he has the full unitary evolution, he has this state, and then either he knows already with certainty, but can also verify, perform this measurement, and confirm that the system and a friend are in this state with certainty. Furthermore, we can even ask something which is here written. What is the conditional probability that the Wigner see yes outcome given that friend saw spin up? Now, Wigner can, knowing and understanding quantum mechanics, say, well, I don't know which outcome friend has seen. I haven't seen this outcome. But if I look and I model my unitary evolution as a measurement of the friend, well, I will know that the friend will see either one or the other outcome with spin 1/2. In each individual run, I don't know what she saw, but I'm sure that she saw in half of the cases spin up. And then I can say, well, no matter what she saw, whether this is spin up or spin down, even this conditional probability will be probability 1, because I'm sure in every single run I will get this with probability 1, and I can even confirm this in a measurement. So this is a non-problematic type. Now,
1/2.
no, it's not.
No, there's a red question mark.
Well, this is your answer. This is your answer. So unfortunately, I really don't like that it's a PDF, because I reveal everything what I want to hide and make a picture out of you. But OK, you have chosen 1/2. So I think there are three possible answers of friend. He can say, I don't want to make a prediction about that, because it's quantum theory forbids me to make a measurement on myself. Because of, I think Philip also mentioned his talk.
The friend.
The
question for the friend.
Well, for both of them.
Oh, for both of them.
For both of them, and now I'm in this.
Okay.
And for example, friend can say, I don't want to make this prediction, because there might be some self-referential problems. I simply deny to give any answer. Or you can say, I don't know, if I see spin up, why can't I say that my memory is in the state that I have saw spin up? And then I look at quantum mechanics and look at the overlap between this state and this one option, and says, well, it's 1/2. Or I say, well, maybe I should perceive that it's possible that Wigner has a full information that I'm in this state anyway, so it will be 1. Okay, so I think these all question answers have only meaning then if we have an experimental procedure for the friend to test this. And here is a very simple one. What we can do, the friend can perform this measurement again and again and again. Now we are talking about preparation of the same state of the spin, what was x plus, again and again and again. And interesting, this measurement is a very trivial measurement. This measurement is such that the state at the end of each measurement run is an eigenstate of the measurement operator. And therefore, this measurement doesn't disturb the Wigner's measurement doesn't disturb the state. So a friend will not know whether Wigner even performed the measurement or not, because the state is the same all the time. So they can repeat this procedure, friend looking at the local result, seeing spin up, spin down, whereas Wigner will always confirm the state with perfectly. Oh, it's yes outcome, yes outcome, yes outcome. Now what Wigner can do, can write down on a piece of paper and send it to the friend. And it is friend who can have both these pieces of papers and then read out these conditional probabilities. For every time she saw spin up, she will see what is the probability for yes, and this will be probability all the time. So there is an experimental procedure, I would claim, for a friend to test this experiment or conditional probability and to convince herself that is 1. It's not 1/2. And there is nothing wrong in accepting this. Sorry.
But isn't that always like another measurement that you're introducing by exchanging information?
This information doesn't contain any, it's not forbidden because it doesn't couple with any of the results. It's just a piece of piece of matter that doesn't correlate with the system, that have no interaction with the spin or with the friend or at. This is information that could be useful for any possible amplitude the friend is inside and will not get entangled with the friend.
But even if you project, it wouldn't change anything.
It wouldn't change anything.
But so the friend does not read it?
It does read it. Does read it.
But that
Later.
changes it. Oh,
But later.
Later.
So
after
formulation-
everything.
After
Everything
and repetition, it
automatically
reads. But
changes.
even it doesn't change because in both amplitudes, this is the same message. It will, if I think about amplitude, spin up, ISO spin up, spin down, this message factors out. It's the same message for everybody and doesn't entangle, doesn't disturb the state. Okay, but they can do it afterwards anyway. So I would claim there is, well, very special case, a yet operationally well-defined, in which the friend can convince herself that it's 1, and it's not 1/2, and there is nothing wrong in doing that. Okay, so now we have a little bit of problem, because it seems that sometimes friend should adopt Wigner's quantum state assignment to make her predictions, and most of the time, not. Most of the time, when she makes a measurement within the lab, she should use the state update rule. But sometimes she should use Wigner's state. So what's wrong? And is there any procedure in which there is a well-defined way what state to use in all cases? And that's exactly what this paper is about. Now I'm finally going into the mathematical formalism behind that, and to the Page-Wootters timeless formalism. So I have certainly no time to go into great detail of that, and we have heard already previously, but Page and Wootters suggested this formalism to address the problem of time in quantum gravity, where the Wheeler-DeWitt type of inequalities boils down to the Hamiltonian constraint that the physical states are such that annihilate Hamiltonian. And if you plug this naively in the Schrödinger equation, you see that there is no evolution in time. And what you get, and then we'll go into this in briefly in several slides, this formalism assigns one timeless state from which probabilities can be computed without the need to involve quantum states or change after the measurements or evolve them in between. There is this static object from which you compute all probabilities. Probabilities earlier and later, we will understand what it means, without evolving the state. There is no any more dichotomy in the formalism between unitary evolution and the state update rule. And then idea naive is that maybe this will help us to simply, to simply have a probabilistic rule which will now not anymore now be dependent on that, whether we accept that there is a reduction of the state or not reduction. Okay, that's the idea. So we use the most simple case where we have a Hamiltonian of the clock and the system, and there no interaction between them. And you know that we need, in order to construct from the kinematical Hilbert space, perform certain operation to characterize what are the physical Hilbert space states. And I will call this operation, which is written here, a projector, although this is not mathematical projector, but just in the language when I talk in the several slides later, I will say projected on the physical states. I will also use a clock state that's a covariant time that Philip was already introduced, and furthermore that the states of the different clocks are orthogonal, so it will be infinite dimensional Hilbert space, where basically the Hamiltonian of the clock will be a momentum, and the time will be position. Okay, this is a very nice picture taken from Giovannetti, Lloyd, and McConnell paper, in which you can think about these physical states as really an object in 3+1 dimension, where you have the superposition of all histories, and the way how you to read this is, if you are interested in what is the state of the system at time t, you slice this at t0 here, and you read out the usual Schrödinger state at time t. The thing is indeed that when you say that the state of the system at the time t, what you mean with this is, well, the time is what a clock reads, so that you mean a joint state of the clock and the system, condition the clock being in the state t. So really, the thing that the Schrödinger state is read from the physical state when you project on a certain time t, and you see then that if you parameterize this state with the parameter t, it satisfies the Schrödinger equation with the Hamiltonian of the system. So you can get back your unitary evolution if you want, but all is encoded already in the physical double cat state. Okay, now you want to get some probabilities out of that. And there is a long discussion on that in the past, but there seems to be no problem in defining the probability for the single event. So single time probability, you can ask what is the probability to observe m when clock shows t. And then what you see here is some, like in general, P of m element, m, time t, and sandwiched with a physical state properly normalized. Now the real problems, and that's what we want to use in the Wigner-Franz scenario, is if you have a conditional probabilities. And if you will blindly extend this into the conditional probabilities, where you via Bayesian rule decompose this conditional probability into the joint defined by the one of those, then you will have here what you see like one P of m element with one t here again, which is sandwiched with a second measurement for P of m element m and some measurement t2. What you will get is basically a delta function. And that was the Kuhar's criticism of this approach, that you cannot get the conditional probabilities right. It's not what you will expect that once you measure n, you evolve with some, well, unitary, if it is not trivial unitary, until t2, and then you measure m. This is what we know from the standard quantum mechanics, and that seems you cannot get this correct. Now, there were several proposals and long discussion. I think even Carlo has one paper on discussion of that. And so I will jump over all this history of long discussions and come to one of the most recent proposals how to overcome this problem. And this is in already mentioned Giovannetti, Lloyd, and McCone paper. Can I ask you how much time do I have?
Yeah, so you're on 27 minutes right now.
Okay, I'm going too fast. Okay, so what you see here is the idea to purify the measurements. And so what how you can do is to include the interaction with the measurement apparatus in the Hamiltonian constraint. So not only that I have now individual evolution of the clock of the system, but you also have interaction between the system and the measurement apparatus included in the Hamiltonian constraint. And you also turn on this interaction at some very particular time Tm. Now, if you think about a graphical representation, you have a system, you have a clock, and at time Tm, you turn on the interaction of that type with the apparatus, which in general, if you have a product states of the system and some memory zero state of the apparatus, you, after interaction, you have entanglement between the system and the measurement apparatus defining different outcomes. Now, if you have this Hamiltonian constraint, then the physical state will look like that. It can be decomposed into two integrals, one between the minus infinity time and time Tm, in which you have the clock and then the product states. That's all what we have is before the interaction, and basically we put this, all before the interaction, sorry, and after the interaction, you get this entanglement that I already introduced here. Okay, and then you can first do and repeat what you expect in a single event probability, just to check that everything is fine. Indeed, when you apply this previous formula for the single event, you get what ordinary quantum mechanics does. And this is more or less in quantum information known as a purification of the measurement. Okay, now I go into the sequence of measurement. Okay, Now, the only one is now added here is that you have actually two measurements at two different times. So you switch on interaction T1 and T2. And you have then interaction between one measurement apparatus with the system and another measurement apparatus with the system. So I have this first interaction, apparatus M1 and system, and then second interaction, system and apparatus 2. And then the integral develops into three parts: no entanglement until T1, from T1 to T1, all entanglement with apparatus 1, and from T2 then entanglement both with apparatus 1 and apparatus 2. And the way how you can now define what is the conditional entropy is very natural extension of what we had before. Namely, this could be a joint probability at T2 after the second measurement has been completed. And then you have both P of M elements N and M for the both apparatus normalized by the state telling you that you have observed the measurement outcome M at T1. Okay, so these are all cases which are non-Wigner friend scenario cases. And we have now a way how to compute this in a timeless formulation of Page-Wootters. So now important thing is that this doesn't tell us anything about how to compute probabilities in a Wigner's friend scenario, because the Wigner's friend scenario is not of that type. What you have in a Wigner's friend scenario is that the second measurement is not only on the measurement of the system alone, but also on the system and the measurement apparatus M1, which is the friend. And we'll come back to this. And so we are not sure anymore whether we can apply the same procedure like here to compute these probabilities. Now I want to compute these probabilities for a very specific case, slightly general than the explicit example that I introduced before. Namely, I will assume that the initial state of the system is some superposition, not necessarily 1 over square root of 2, but some AB, and we can take them to be real numbers because we want to make it simpler, but in the paper it's more general. And we will also assume that friend measures a spin along z direction, so really in this direction. Wigner's will still measure yes, no observable, but a projection on a yes will be a projection with alpha and beta. So previously it was 1 over square root of 2, but now you see that this number and that number could be different. And that's very important because it's more general. If you have this state, and the friend gets entangled with this state after measurement from the Wigner's point of view, they will have A up, up, B down, down. But I will also want to measure something which is not commutative with this, and I put here alpha, so somewhat different. Okay. Now, this is the situation in a Page-Wootters formalism. The prescription is the same. The situation is different, as I said, because the friend gets entangled, the friend's memory gets entangled with the system at Tf of measurement of the friend. But at Wigner time, Wigner entangles the system and the friend measurement with his memory or with his measurement apparatus. And this is included in the Hamiltonian constraint. And we again have this decomposition in 3 different times. No entanglement, entanglement with the friend's memory, entanglement with the Wigner's memory. But it remains open how to define the probabilities. So here is one example that we have chosen. And you don't ask me why we have chosen it. There is some, and I will try to argue that there is some kind of symmetries in this, and that's why we have a very idea of that. But unfortunately, we don't have any systematic search for all meaningful Born rules. Here is one Born rule. You can say, well, I like always to make the first measurement. This is the measurement after the first, this is the state after the first measurement. This is the state after the first measurement. And then I apply this on the P of M element of the second measurement. This is the ratio behind this choice. Now here is something to see. This would be the state after projecting on P of M and T1. But since this projection can get the system state outside of physical states, such that this state does not satisfy the Hamiltonian constraint, we put back this projection that brings back the state into the physical state. And then we may perform the second measurement. So the blue part is the second measurement. And we properly normalize by the probability to obtain at T1 M, which is the Franz measurement. Okay, so here's a few things that I want to tell you about this. This probability is always well defined. Namely, it's positive and normalized. It thus corresponds to the state update rule. So this really projects the state. If, and I will go into this discussion later on, if both of them apply this rule, this will correspond, and if there was an objective collapse of the state at Franz measurements. And it's reduced to the standard probability rule that I have introduced for all non-Wigner Franz scenario. So it's a possible extension.
Does this prevent Wigner from seeing interference between the two branches?
It prevents. He will then see the probabilities that will be 50-50 for his results, yes, no.
So in this sense, violate one way.
In this sense, it can be operationally distinguished.
Yeah.
And I would say we leave for the experiment to decide.
No, right, but sure. But it violates the assumption that quantum mechanics is exactly true for Wigner.
I would agree with you, but I would also say that this is a slightly different type of measurement because really the Wigner, it violates, I would say, equivalence between all systems and will need somehow to adapt when you also measure memories. But I agree with you. And I'm not in favor of that. I agree with you.
I actually may want to comment on this later on because this is actually the version you get from the equivalence between the different formulations of relational quantum dynamics. So this is actually the one you get from relational observables. I comment on this later.
Okay, I will be interested. Okay, so this is something which corresponds to collapse. So if indeed Wigner performs yes measurement and friend has either spin up or spin down, these are the combinations. So let's take one of them. Let's say if friend saw spin up, that means it's with certainty in this state. What is the overlap with this state with the yes? Oh, this is alpha squared, so this is this alpha squared. So this corresponds really, and both can use the same Page-Wootters formalism and conclude that this is the result. And both even can get convinced by measuring results, sending them into back to the friend that this is true, if it is true. That's another one, which I slightly prefer more. This one also has rationality is that you simply have an overlap probability, this state with that state. Again, you put a projector because it can go out of physical state, and this is what the state after the first measurement is, and this is what you wanted to check the second one. This is not always well defined. That's very interesting. This is only then well defined where the measurement operators commute on the physical state when compared at the same instant of time. So if this is a projector on the maybe I mixed it. So you have to evaluate one of those projectors at the time when you measure the other one, and if they commute on the physical state, then the probabilities are well defined. This boils down in our case exactly when A is equal to alpha and B is equal to beta. This is very indicative. You remember that when alpha and A were not the same, the measurements were not commuting. In other words, what will mean is that when Wigner performs measurement, it disturbs the memory of the friend. And I don't like to make any operational statements on friends receiving some message from the Wigner once the memory is disturbed. I think it is an interesting question. There's more to be learned from that situation. But for sure, when this doesn't happen, is exactly situation in which friend can receive the message from the Wigner, no disturbance, and really compare this, and they both can agree that probability, the probability is 1 for yes outcome. I will see in the next picture. And it also reduces to the standard probability rule. I'm concluding. This is now our situation. I call this unitary conditional probability just to make a difference to the collapse one. And this is the case when alpha and A are the same. And then both of them can apply this rule, and they both can convince that this is the probability 1. Even when friend sees spin up, friend will say, because the measurement is on me and the system, I deny to use state update rule. I use the Page-Wootters timeless formalism, and I compute this as 1. And this has an operational meaning, because Wigner can send the result into friend's laboratory, and friend can compare both lists and say, oh, it's indeed 1. So the lesson is there is no necessarily, there are, if you want, 2 states for 2 different situations, but they are both part of the Page-Wootters formalism. They both can use Page-Wootters formalism and compute the probabilities as long as they wish. They can compute until my friend's measurement, which will be the same as a collapse. They can go on until Wigner's measurements, and they will get this result. Okay, and with this, in conclude, there were several definitions for the conditional probabilities for Wigner friend scenarios. There are more in the paper, but these 2 are most appealing. All of them are equivalent for standard non-Wigner friend scenarios. There is a need to classify them and to look at operational meaning for each of them, maybe to reject on the basis of logical inconsistency. What is completely missed with this approach is something I think also Philip is interested. Is there a way to have a more balanced view? This sounds like a slightly more balanced Wigner view how to deal with this. But can you have something which is more perspective dependent and then give the same description from the friend's point of view? Thank you very much.
I could have used my power and I want to comment, but no, first, I think Marco was first, and then was I first? I thought so.
Okay.
But anyway, I mean, how to get to say something.
So if I understood correctly the framework, basically the way to understand the Wigner's friend issue is that Wigner uses the ordinary Born rule to make predictions, while the friend uses this modified from the Page-Wootters formalism, and then they agree with the results in a sense, right? So I mean, you can go back one slide. Basically, that's what. So if the friend uses the Page-Wootters definition of the Born rule, the modified definition of the Born rule, then
This one, the unitary.
yes. Well,
Yes.
then the friend will conclude that regardless of the fact that he sees various results,
Yes.
he actually knows that he's in a superposition state as Wigner's message
Yes.
would confirm. Yeah. Okay. So my question is about additional nesting. So Wigner is using the ordinary Born rule, but you can put the whole thing, Wigner and the friends, on in another box,
Yes. So
and then Wigner is not supposed to use the ordinary Born rule, but again this Page-Wootters unitary
Yes.
rule.
Yes.
So
for all the measurement that goes beyond, that will involve his memory.
yeah, so I think that that's just pushing this problem of where do you make a cut, further outside of the. I mean, you can always whatever physical system you have, you can always imagine that it is in a box and being measured by something else.
I think there is no problem with this. There is a Page-Wootters formalism. You ask me, which questions do you want? Do you want a question about my system in lab? I calculate until this point, I give you the results. Do you want something which involves my memory? I calculate a little bit further. And they all do the same, and they all agree on that. But I don't like the
Yeah, I
formalism.
can-
Can I say that I don't like the formalism? Because it's this from above. It's very much many world. I know.
Are you done? Then
I think it can be improved.
Yeah, actually, Marco, I wanted to say half of what Marco said. This was it's a great talk. I love this. How do you react to that in Marco's perspective? You're asking what the friend has seen and what the Wigner has seen, right? That's the question. How you put them together in this specific measurement. We know what measurement they do, and let me take alpha and beta different from AB because the case alpha beta equal AB is sort of simple. So let me take the hard case. Alpha beta. And let me give you a solution, and I want to know what you think about the solution. Solution is Marco's solution. So now there's friend Wigner and Caslav. And Caslav wait for everything to happen and then compute what he's going to measure and uses quantum mechanics for the full thing. And then Caslav made two measurements. One is, hey friend, what have you seen? And one is, hey Wigner, what have you seen? And now Caslav discovered, if I believe the quantum mechanics too, that whether he asked first the friend and then Wigner, or first Wigner and then the friend, he gets different results, which we know in standard mechanics textbook because if you measure x and p, you get different than measure p and x. So that seems to be saying that the question is well posed. Only the question of what the friend and Wigner both see is only well posed with respect to the Caslav observer, and by themselves is exactly the same question of asking what is the position and the momentum of the particle at the same time, the answer being there isn't, because there's no procedure for doing that. There's no friend knowledge and Wigner knowledge together. They are non-commutative things. They don't either one or the other, or one and then after the other, and then or first measure friend and then measure Wigner, or first measure Wigner and then friends. That seems to be consistent, and I expect you would agree with that.
Yes,
You would.
I agree that. We go a little bit beyond. I was talking about really operation well-defined in quantum mechanics conditional probabilities. What you're talking, you're going beyond that. You're saying, is there a joint probability for both of them seeing what they have seen? And there is no.
There is not.
There is not. But here is more or less, here is operation which I even try to give an operational procedure where they can measure that, they can prove that.
But your visualization is only in the case alpha equal A and beta equal B, not in the general case. You didn't
because is that for friend there will be a problem because friend performs at T1 one measurement. When at T2 I perform this measurement where alpha and beta, alpha and A are not the same, I will change the memory of, I will change the memory of the friend such that there is no any more meaningful definition of conditional probabilities. What is the probability that we're gonna see this if I have seen that the procedure as sending back will not be the same. It will give some numbers, but these numbers will not correspond to what she has seen really at T1 because in the meantime the memory has changed. And that's a very indicative. Formalism tells you, hey, there is no meaningful conditional probability exactly in these cases. They are only in these trivial cases when they can compare.
Yeah, I also wanted to, or maybe I'll comment last, so then maybe you go first, but quick question.
Yeah, thanks for your interesting talk. So I was wondering, is it why can the friend not also use the Page-Wootters formalism?
It can. I tell everybody has.
But what's
the
the condition on using this formalism? The beginning is like Hamiltonian acting on the state equals 0, no? So.
Oh, sorry.
Counterintuitive.
It's counterintuitive, yeah. So I would say they both use this constraint, and friend wants to make a prediction about measurement within the lab. He stops here. I say I can use this. I mean, he can use, of course, ordinary quant, but he can use this. Stop here and make prediction. And someone say, oh, I want also that you tell me something about the measurement on your memory. He computes until that, check what you want to measure, and say, I'm sorry, I'm not sure I want to give you an answer, unless it's a very trivial measurement in which I can give you an answer. and I compute until then and give you an answer.
Wait, so the formalism is only valid if psi if the state psi satisfies this condition?
Yes.
Right.
There is a very important thing. This doesn't mean that there is no. I was concerned with that. I don't know whether everybody, that this somehow is very strange. In quantum mechanics, we have a Hamiltonian, which is outside the laboratory, and we have free choices within the laboratory and choose operations. Here, we embed them in the Hamiltonian. Now, my way of thinking is that still it's preserved, the free choice, because you can have free choice here what you want to put. It's just procedure how to compute this. It's different than in standard quantum mechanics. But it's not that you are fixing in advance what you were going to measure.
Okay, let me maybe briefly comment on these different conditional probabilities, because so this was one thing that I actually wanted to discuss in my talk, but of course I didn't manage to finish it. So, I mean, what we have done in our work is now really have the systematic dictionary between the physical Hilbert space and the relational dynamics in terms of relational observables on physical Hilbert space, and then the conditional state formulation, this relational Schrödinger picture from Page-Wootters. And it really cleanly separates the different formulations and gives these reduction maps in between. And that allows us to systematically derive also conditional probabilities in the Page-Wootters formulation from the natural one on the physical Hilbert space. And so there's a systematic way of doing that. And on the physical Hilbert space, there's a very natural way of imposing conditional probabilities in terms of relational observables, constructed also for sort of projection kind of observables, and that actually leads to Dolby's formulation.
To the first one?
Well, no, I guess.
Collapse? Or?
Well, the other one by Dolby, I mean, this was your first, I guess, but I guess it's your second.
In the papers.
This one here.
This one.
Yeah, so it leads to this formulation. So it turns out that these objects here are actually relational observables. And I mean, that naturally leads also to the resolution of Kuchar's criticism, and without adding any degrees of freedom. So it's just from the degrees of freedom you're a priori interested in, that resolves it.
So what you're saying, there is a natural way that they get actually here collapse and not unitary probabilities.
No, I'm just saying there's a natural way of deriving that conditional probability from the physical Hilbert space.
So that you mean that in
the
this
gauge
experiment this will show collapse then, or?
No, that's not what I'm saying. I'm just saying that if you want to have a systematic derivation of what are the conditional probabilities coming from gauge-invariant formulation, then it's this one, the Dolby version.
Okay.
Yeah, I don't know if there's any other
Just
questions or
one very
comments.
sorry, shut up. I talk too much. When Wigner makes his measurement with alpha different from A, is interacting with the friend.
Yeah.
So
the
there is
apparatus
some,
is interacting
there's some
with the friend.
dynamics.
There is some dynamics, yeah.
So nothing tells us that the friend conserves the memory, given that the memory is one of our variables.
It does not. I think
It
even
does not.
It does not. I think even
So it's actually really in this setting is actually messing up the memory of the friend.
it's actually met unless alpha.
Unless alpha equality.
Yes, and I think if I may 2 minutes address again your point of having different levels of Wigner. There is a conceptual little bit, or tension is a little bit stronger than in XP measurement, because all the time the friends can say, I have performed measurement. Even when the memory has changed, she will still say, I have performed the measurement. It's just that an instance that she thought that spin up will change and spin down. And the no-go theorem about no observer-independent facts can be read in that way. In that way that if she would keep the memory after opening the box, like it can be either this measurement in the superposition basis, and she memorized something, and the other complementary measurement is the Wigner opened the box. If she would keep the memory after opening the box,
You destroyed interference in it.
yeah, this is true. But if you would have some kind of Bell experiment in which you either choose this measurement or that measurement, and if a friend will keep the memory after opening the box, that would really means that there is a joint probability, because he performs some measurement, she performs some measurement, so you think there is a joint probability. She can even send to Wigner and say, I have performed the measurement. So the Wigner says, oh, we have a joint probability. But if this is true, and he decided not to perform this measurement, like in a bell type, but to open the box, and she would keep the memory, what has been before, in her memory before the box, this would mean that there is a joint probability in which opening the box just marginalized this thing. Because there was a kind of joint probabilities when they measure different things simultaneously. He opens the box, marginalizes this probability. The fact that you can exclude this tells you she has to change the memory.
Okay, I think we now need to stop this because we're totally running over time, so let's thank Caslav again.